To embark on a journey through the universe's deepest origins, we must listen to the faintest whisper that permeates all of space, a subtle, pervasive glow known as the cosmic microwave background, or the CMB. This is the oldest light in existence, a remnant from a time when the cosmos was young, hot, and unlike anything we see today. The CMB is a ghostly afterglow of the Big Bang, a relic radiation that tells the story of the universe's birth and its first moments of transformation. The universe we inhabit, with its vast galaxies, twinkling stars, and swirling nebulae, was not always like this. In the beginning, space was filled with a dense, searing plasma where matter and radiation were indistinguishable, a swirling sea of energy so hot that atoms could not yet exist. Light could not escape. It was trapped in an impenetrable fog, scattering endlessly between charged particles. But as the universe expanded and cooled, something miraculous happened. This primordial fog lifted, and light was set free to journey across the cosmos. The photons released at this epoch have traveled unimpeded for nearly 14 billion years, stretched by the expanding fabric of space itself to microwave wavelengths. This cosmic microwave background is a snapshot of the universe in its infancy, the oldest picture we can ever hope to capture. The story begins at time zero, the moment we call the Big Bang. Although bang implies an explosion, it was, more accurately, the rapid expansion of space from an unimaginably hot and dense state. At that moment, all the energy and matter that now fills the cosmos was compressed into an infinitely small point. In the first fractions of a second, the universe was unimaginably hot. Temperatures soared to trillions of degrees. Under such extreme conditions, particles like quarks and gluons existed freely, before cooling allowed them to combine into protons and neutrons. In this primordial soup, photons, the carriers of electromagnetic radiation, were trapped, continuously scattering off free electrons and other charged particles. This era, called the photon epoch, was a cosmic dance of light and matter, locked tightly in thermal equilibrium. The universe was opaque, filled with a glowing plasma where light could not travel freely. Imagine trying to see through a thick fog. Light is scattered and absorbed constantly, preventing any clear view. As space expanded, the energy density decreased and the temperature fell. After about 380,000 years, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. This moment, known as recombination, changed everything. Suddenly, photons could travel vast distances without being scattered. The universe became transparent for the first time. The light released during recombination is the cosmic microwave background. It's a fossil imprint, carrying the conditions of the early universe across billions of years and light years of space to us here and now. For many decades, the idea of the universe having a beginning was contentious. Competing models, such as the steady-state theory, proposed an eternal, unchanging cosmos, continuously creating matter to maintain a constant density. The Big Bang theory, in contrast, suggested a dynamic origin. The existence of relic radiation from the Big Bang was predicted in the 1940s and 50s by theorists like George Gamow, Ralph Alpher, and Robert Herman. They reasoned that if the early universe was hot and dense, then leftover radiation should still exist, cooled and stretched by cosmic expansion. However, this faint glow was not detected until 1965, when Arno Penzias and Robert Wilson, working at Bell Labs, encountered an unexplained microwave noise in their radio antenna. This signal was isotropic, coming uniformly from all directions, and had a temperature around 3 Kelvin. After ruling out every terrestrial and instrumental source, and with the help of physicists at Princeton who had been searching for this relic radiation, the two scientists realized they had discovered the CMB, providing compelling evidence for the Big Bang model. Their serendipitous discovery transformed cosmology overnight and earned them the Nobel Prize. Once the CMB was discovered, cosmologists sought to study it in detail. The cosmic microwave background is remarkably uniform, but it is the tiny temperature fluctuations, anisotropies, that hold the key to understanding the formation of cosmic structure. The first satellite mission dedicated to measuring these fluctuations was NASA's COBE, Cosmic Background Explorer, launched in 1989. COBE confirmed the CMB spectrum was a nearly perfect blackbody, as predicted by theory, and detected temperature variations at the level of a few tens of microkelvin. This achievement was a triumph for cosmology and earned John Mather and George Smoot the Nobel Prize in 2006. Following COBE, the WMAP, Wilkinson Microwave Anisotropy Probe, satellite launched in 2001, producing higher resolution maps that revealed finer details of the temperature fluctuations. MAPS data allowed cosmologists to precisely measure the universe's age, geometry, and composition, including the relative amounts of ordinary matter, and dark energy. Most recently, the Planck satellite, launched by the European Space Agency in 2009, has provided the most detailed and precise maps of the CMB to date. Planck measured both temperature and polarization anisotropies across the entire sky, improving constraints on cosmological models and deepening our understanding of the universe's earliest moments. The tiny variations in temperature observed in the CMB are the seeds from which all cosmic structure grew. These fluctuations are incredibly small, about 1 part in 100,000, but they represent slight differences in density, pressure, and gravitational potential in the primordial plasma. These primordial perturbations originated from quantum fluctuations, tiny variations in energy present even in a perfect vacuum due to the laws of quantum mechanics. During inflation, a brief period of exponential expansion shortly after the Big Bang, these quantum fluctuations were stretched to cosmic scales. As the universe expanded and cooled, gravity amplified these fluctuations. Denser regions attracted more matter, eventually collapsing into stars, galaxies, and clusters, while less dense regions became vast cosmic voids. The CMB's fluctuations thus contain a fossil record of this initial cosmic landscape. By analyzing these anisotropies, cosmologists can reconstruct the universe's composition, its rate of expansion, and test theories about its origin and evolution. In addition to temperature variations, the CMB is polarized. Polarization refers to the orientation of the electric field vector of photons. The CMB's polarization pattern contains even more subtle information about the early universe. Two types of polarization patterns are observed: E modes and B modes. E modes, which have a curl-free pattern, were first detected by WMAP and Planck and arise primarily from scattering processes in the early universe. B modes, on the other hand, have a swirling pattern and are predicted to arise from primordial gravitational waves, ripples in space-time generated during inflation. Detecting these B-mode patterns would provide the most direct evidence for inflation and open a window onto physics at energies far beyond the reach of Earth-based particle accelerators. Experimental efforts worldwide, using ground-based telescopes, balloon missions, and future space satellites, are underway to detect these faint polarization signatures. The detailed study of the CMB has revolutionized our understanding of the cosmos. Today, cosmologists believe the universe is composed roughly of 5% ordinary matter, the atoms and particles that form stars, planets, and life as we know it. About 25% is dark matter, an invisible substance that interacts gravitationally but does not emit or absorb light. The remaining 70% is dark energy, a mysterious form of energy permeating space and driving the accelerated expansion of the universe. The nature of dark energy remains one of the greatest mysteries in modern physics. The CMB also reveals that the universe is flat, meaning its geometry follows the rules of Euclidean space on large scales. This flatness was one of the key predictions of inflation and confirms the universe's global shape.